Fluid system modeling. By the end of this section, you should be able to find the analogous resistances, capacitances, and inductances in fluid systems, model fluid systems using electrical analogs, and with the model, be able to create transfer functions when the input or the output is a flow or a pressure, and use Simulink to simulate solutions to these transfer functions. The approach we're going to take to modeling our fluid systems is going to be by creating electrical analogs. So basically, we are going to find analogous elements in our fluid systems to those in electrical systems and then model it just like we would electrical systems from the previous section. So first, as with the mechanical systems and the electrical systems, we are always analyzing our systems when they are perturbed from a steady state. So technically, what we are going to be looking at for our inputs and our outputs is a change in either flow rate, specifically volumetric flow rate, or a change in pressure from the steady state values. Now that steady state may have been that all of the flow rates were zero, all of the pressures were zero, and now we are starting to fill up our system with fluid, or we could have a system at steady state where just the pressure is non-zero constant, and the flow rates were a non-zero constant. But all of our analysis is going to be based on small changes from this steady state. And this is not different than what we were looking at with mechanical systems or what we were looking for in electrical systems. In both of those, also, we were looking for changes from the steady state or changes from equilibrium. However, the language we're going to use is usually just calling something the flow rate or the pressure, but technically it is a change in those things from the equilibrium or steady state values. So how do we turn our fluid systems into electrical systems? Well, we're using these electrical analogs. So we'll get into more details of how we calculate all of these analogs in a moment, but first we want to see what are these one-to-one correspondences. So first, we're going to see that the pipes in our fluid systems are analogous to wires in our electrical systems. Now, all the wires we saw in the electrical systems, we were assuming had no resistance in them, they had no inertia, and they offered no capacitance. Now, in reality, wires are going to have some resistance in them, and it's going to vary depending on the cross-sectional area of the wire, the resistivity of the material in the wire, and things like that. We treat them all as having no resistance. It will be different in our fluid systems that we will often want to include certain things in the pipes in our system. For example, the wall resistance of our pipe from the fluid going across it, we might include as a resistance. And also the inertia of the fluid traveling through the pipe, we also might want to model because that is going to have some effect on our system. So in this case, pipes might offer resistance and equivalent inductance, whereas in our wires in the electrical systems, we ignored all of that. The fluid system will have a volumetric flow rate, usually denoted by Q, and that will be analogous to our electrical systems, the current. In the electrical systems, the current can be thought of not quite correctly, but we can generally think of a current as the flow rate of the electrons through our elements, through our wires. In the fluid systems, it's going to be the volumetric flow rate of whatever our fluid is, through our elements and through our pipes. We're going to have pressure or head pressure, and that will be analogous to the voltage or the potential difference. Again, in the electrical systems, voltage and potential difference in a way is how hard the electrons are being pushed through our wires and through the elements. In fluid systems, that's actually going to be true. The pressure is how hard the fluid is being pushed through our different elements and through the pipes. The inertia of the fluid is going to be analogous to our inductance. And we're going to see that by the impedance values we're going to find for fluid inertia match those that we see in inductance, whereas it's going to be our current, or in this case, our flow rate, times an S term times a constant. tanks are going to be analogous to our capacitance in that, again, the impedances are going to look similar. We have a 1 over S term with our capacitors. When we are in electrical systems, we're going to have a 1 over S term in our tanks. And then wall resistance or valve restrictions are going to be analogous to resistance. And again, thinking to our electrical systems, resistance, its impedance was just R. There was no S term at all. So just this R times our current. We're going to see that our resistances in fluid systems is also going to be some constant times our flow rate. So mathematically, the inertia and the inductance are going to be paired. The tanks and capacitance will be paired, and our wall resistance and valve restrictions will be paired to the resistors in our electrical systems. Now, we are also going to have to worry about the sources like in our electrical systems. The electrical systems, we typically had a voltage source in the examples that we looked at. However, we could have also had a current source. In our electrical systems, we are often going to see current sources in that they are analogous to our input flows. So fluid coming into our system, or potentially fluid coming out of the system at a prescribed rate. Those will be analogous to a current source. And when we have output flows going out of our system into the environment, into the atmosphere, we can treat those as sinks, in that all the output going out into the environment can be drawn as going into ground, where we have zero potential, or at least zero relative potential compared to our system. Now, along with current sources, we could have voltage sources in the case of a pump or something that is going to be applying a pressure into our system. But more often, we're going to see these input flows and therefore current sources in our electrical analogs. And just to remind us what we're looking at, we're going to be writing, and I'm going to be saying pressure and flow rate. But once again, technically, there are changes to the pressure, changes to our flow rate from the steady state values. And that is what we're analyzing, are these perturbations from equilibrium.